Welcome to this class. So in this class, we'll study about torsional pendulum. So let's look at this diagram drawn here. So we have a rigid support and we have a small disc over here, which is supported by the mean of certain wire of length L. So this wire, we can treat this as a solid shaft to which this disc is being attached. Now, if we displace this particular disc in horizontal plane by certain couple, a twisting couple, so it can produce a twisting moment in this particular wire. And if we leave it, then it will keep performing oscillations. This disc will keep performing oscillations, and that's why we call this as a torsional pendulum. Okay, so whenever we apply a twisting moment, we certainly apply certain external force, external kind of twist, not force here, as we are seeing the torsional pendulum. As we are applying a deforming couple, the system will act. So system will respond to the deforming couple, and it will produce certain restoring couple. And this restoring couple, we have to see and get the expression for the differential equation for the torsional pendulum. So let me write down the certain terminologies first, which we are going to see it here. So the variable, the displacement variable in our case would be theta. So theta is angle of twist. Theta is angle of twist as we are deforming and we are basically twisting the wire, supporting wire. That's why it will produce certain angle of twist in the wire. So we have denoted by this theta. Theta is angle of twist, which is our displacement variable. We call this as displacement variable. This is our displacement variable. Okay. So L is the length of wire. L is length of wire. And this wire will have a torsional rigidity. Torsional rigidity. So as we have produced a deforming couple, now we are applying certain external couple on this particular system. Deforming couple will lead the system to react, and system will respond to this deforming couple through equal amount of restoring couple. Equal amount of restoring couple, which will try to get this particular system as we have deformed it to the original shape or original position. So basically it is a kind of force balance, not a force balance. For your sake of understanding, I'm calling it as a force balance. This is basically a torque balance, right? So this is basically twisting, as you have seen, you must have seen in this particular simple pendulum thing. So we had a simple pendulum. You have a simply supported, this bob is supported by wire. If you displace it, so your forces are means unbalanced. So this will try to again come back to this particular thing. Similarly, in simple harmonic motion, suppose if you have this particular block over here, spring is attached. If you displace, so this is mean position. So if you displace from mean position by certain amount x, then you have deformed this particular system. So system will respond to this deforming force, and it will produce an equal and opposite restoring force in opposite direction, so that it can come back to its mean position. So exactly analogical, in torsional pendulum, you are producing, you are applying a deforming couple. So to come back to its mean position, system will produce a restoring couple which is of equal amount but in opposite direction. This would be equal and opposite. This is important. Equal and opposite. So what is this restoring couple? So this restoring couple is equal to this restoring couple would be equal to, last lecture for the equation of torsion we have seen that twisting moment, which is nothing but the couple per unit twist, is called torsional rigidity. So this twisting moment, which is nothing but a couple, we can call it as a couple, restoring couple, is given by c times theta. C times theta. So this is torsional rigidity. Theta is the angle of twist. Now this is in opposite direction. So I'm going to put this minus sign over here. So due to the inertia, due to the inertia, now system will respond, and due to inertia, we are going to see restoring couple would be equal to what? So this is your applied this thing, and due to inertia, we have this couple balance here, couple balance. Now we are going to write a couple balance. So how to write a couple balance here? So this is a kind of deforming couple C theta, which we are applying through certain twisting moment we are going to produce, and system will now react to this with equivalent opposite torque. Okay, so what is that? So we'll see it here. So I'm going to write the analogy for your sake of understanding. So restoring force in case of spring, restoring force was equal to kx. So opposite direction, let me write this at the last. And your system inertia will give you, this is nothing but this restoring will produce acceleration to the system, and this is nothing but mass times acceleration, restoring force. So this is balance of mass times acceleration and the restoring force being produced. So exactly similar if you write a torque balance. Torque balance. Now this torque balance will lead to our differential equation. So how it leads to our differential equation? So due to inertia, inertial torque is given by I times alpha, where this I is moment of inertia of system. This is kind of mass of system, moment of inertia of system about axis of rotation, because this is moment of inertia. And this alpha, as this is angular motion, this is angular acceleration. So here we had a translational acceleration, here we have an angular acceleration, because we are going to twist this wire, right? So this inertial torque is given by I times alpha, and we know alpha, how to find the alpha, because our displacement variable is theta. So if we differentiate this theta twice with respect to time, I get an expression for the angular acceleration. So I can write this inertial torque equals to moment of inertia of system about axis of rotation times d2 theta upon dt square. And now I'm going to write a torque balance for this. So this is kind of inertia, system's response. We have a deforming couple which is equal to c theta, both being in opposite direction. I write a I write a torque balance as I times d2 theta upon dt square equal to restoring minus c times theta. This minus sign is for opposite direction, minus c times theta, restoring. So I get final expression as I d2 theta upon dt square plus c times theta equal to 0. So this is a differential equation for angular SHM. This is basically a differential equation for angular SHM. So for the linear SHM, you had, instead of inertia, you had mass times d2x upon dt square, translational acceleration, plus spring constant k times x equal to 0. Exactly analogical to this, instead of mass, you have inertia for rotational motion. So I, instead of displacement variable x, you had angle d2 theta upon dt square, plus instead of spring constant, you have torsional rigidity times your displacement variable is theta equal to 0. So this is kind of analogy. So let me write here analogy, translational versus rotational. So in translational, you had mass, you have here inertia. So in translational, your displacement variable x, here you had theta. So in translational, you had spring constant k, you have torsional rigidity c here. Otherwise, these two expressions look exactly similar. So I can write this expression as differential equation as d2 theta upon dt square plus c over I times theta equal to 0. And if I compare with the d2 theta upon dt square plus omega square theta equal to 0, then I can write this omega square to be equal to c upon I. Basically, you can solve this differential equation and you can get the answer for this. That's why we have written this omega here. So let me even solve this in brief. So what we have here, so we have this differential equation d2 theta upon dt square plus c upon I times theta equal to 0. This is second order differential equation d2 theta. So this expression theta as a function of t is a cos of omega t plus b sine of omega t. You can take this relation, or instead you can simply take as a cos of omega t plus phi, because anyway you can combine this cosine and sine term together and you can write this particular expression as this one. Or even you can write, there is no restriction on writing as a sine of omega t plus phi as well. In that case, according to the which expression you choose, accordingly your phi value will be selected. Okay, so if I choose this particular expression and let us find the value of a and omega, so I get d theta over dt would be a times omega times this cos of omega t plus phi, this cos of omega t plus phi. And if I differentiate one more time, this would be equal to a omega square, and cos derivative of cos is minus n, so it is minus omega t plus phi. So this is nothing but, if you combine these particular terms, this is nothing but minus omega square theta. So from this, what you have got here? So d2 theta plus omega square theta, d2 theta upon dt square plus omega square theta equal to 0. And this expression represents what? This expression for the theta angle represents, as this involves sine term here, this is periodic in nature. This is periodic. So basically, as it is periodic in nature, the solution for theta, the expression for theta, which is our displacement variable, is periodic in nature. This is angular SHM. That's why we call this as angular SHM. So we have got this expression. Now, if we compare our differential equation with this differential equation for angular SHM, we get the omega. So angular frequency square equal to c upon I. So the disk is performing angular SHM, so it would be having certain angular frequency, which is now given by square root of c upon I. Now from this you can find different terms like time period. Time period is basically 2 pi divided by omega. So you got an expression for time period equal to I upon c. I upon c. So in translational SHM, linear SHM, you had exactly similar 2 pi. Your this I inertia would be equivalent to mass, and this torsional rigidity was equivalent to spring constant. So what you have already studied. So these are not actually different. You can simply analogically even directly write these terms for the torsional pendulum as well. So our torsional pendulum will have the expression for the period, time period, which is given by 2 pi under root of I moment of inertia of system about the axis of rotation divided by the torsional rigidity. So in this short lecture, we have derived the differential equation for torsional pendulum and then got to know that it is exactly similar to that of angular SHM. So it basically denotes that our system is performing angular SHM, and by comparing our differential equation, what we have got, we have obtained an expression for angular SHM, sorry, angular frequency and the time period. Okay.